have to anyway, off with a summary. We've seen there are two approaches to prediction in events associated with hurricanes and, of course, their impact on coastal regions. One, as illustrated by Carrie Manuel, of abstracting out. What's happening? We have another mic. Okay. All right. Excellent. Okay. So one approach of creating a simplified model, in his case by converting to a different coordinate system based on angular momentum, which then was able, one of its features was able to concentrate resolution where it was most needed. And the net effect was, despite leaving out a fair amount of physics, fairly good predictability or fairly good skill in reproducing events. And it would run extremely quickly, 15 seconds on a laptop, I think you mentioned. And as one of the features of these fast-running models is the ability to run very large numbers of ensembles, which he argued, correct me when I misstep, but he argued that that would help to search for these rare events by running tens of thousands of simulations. Clint's talk presented an alternative, well, not alternative, but a complementary approach of a very high resolution, both in geometry, so very fine meshes, and in solving not the highest resolution models, those would be too expensive, never Stokes, but shallow water, enhanced shallow water equations, and through exploitation of parallel computing resources, being able to turn around calculations. I think everything you talked about was the hindcasting, but I know they've done forecasting for Ike. I think they were trying to run some calculations in real time. And maybe more recent earthquakes. So that's my summary of these two approaches. I guess the pertinent question is, from what we've seen, what sorts of mathematical questions do these approaches engender, and how can that lead to enhanced collaborations between applied mathematics and the geosciences? And maybe I should start off, Clint, summarize a number of the research questions, mathematical research questions, and some of the modeling questions at the end. Maybe I can ask Carrie to do a similar thing, just a short summary of what questions you see, mathematical questions you see associated with your work. Do that. And I guess we're just on this one mic.
So, I mean, one kind of obvious theme that's discussed in many branches of meteorology is uncertainty and how you deal with it. So you can talk about, well, make the models better. There's sort of obvious avenues of research, and I could spend some time talking about that with respect to hurricanes if you like. But there's, I think, maybe a more interesting question for this audience is that you can build, even hypothetically, an almost perfect model, but you always have uncertainties with initial conditions and boundary conditions if you're trying to do something like a forecast. And this came up in the discussion of surges when we tried to forecast, for example, a surge in Houston. And I said, and I think Clint might agree with me, that I would guess that the main uncertainty in a 48-hour forecast is the meteorological uncertainty of where the hurricane will go. And probably the uncertainty is associated with the surge model, I'm guessing, pale in comparison to that. So how do we deal with it? And I don't think that the approach of making the models better, which we should do for other reasons, is necessarily going to get us very far, because a lot of that's initial condition. And that goes into the whole problem of ensemble forecasting, where you make many forecasts and you try to create a PDF of probable outcomes. And then there's an interesting mathematical issue is, if somebody gave you incremental resources, will we put them into making the models better, or will we put them into running more ensembles to get a better quantification of the PDF of uncertainty, or how would we apportion those things? And this is, I think, a very rich avenue amongst the others that we've discussed here, and how to deal with it. It's a really interesting problem of quantifying uncertainty, even if this community solved that problem. Even if we came up with really optimal PDFs you guys know what I mean by PDF. If you try to use that to warn people of a surge, which is why we're doing this in the first place, right? Part of the reason we're doing the first place, the communication problem turns out to be a real nightmare, all right? And a lot of people have tripped over that, and that's maybe not just a problem in sociology, it's a problem in how best to quantify uncertainty. So I think that's something where statisticians, mathematicians, and geophysicists could all kind of try to work together on.
All right, Seth.
Sure. Actually, Tim Palmer has written a beautiful paper about this, which hasn't been published yet, but it's his presidential address. He's the new president of the Royal Meteorological Society in England, and he's written a paper just about this. There's a third approach, in addition to the two you mentioned, which Ed Lorenz had said in the 1960s would be the direction NWP would go, and is to put stochastic terms in the equations themselves. The remarkable thing is that the European Center for Medium Range Weather Forecasts, widely regarded as the best NWP outfit going, ECMWF, some people used to say that meant enormous computers making wrong forecasts, but now they're making the best forecasts. They're actually doing that, and they're showing that the usual metrics of the skill of ensemble forecasts improve when you put noise terms in the equations. And this is really fascinating. I don't pretend to fully understand that, but it's a very, very fruitful avenue in modeling that's just, I think, just beginning to be pursued. And Michael, maybe you have something to say about this too. You probably know more about it than I do, but it's interesting.
In the higher sciences in general, which is a hierarchy of models, not a hierarchy of models in a multi-scale, but a hierarchy of models. From the simplest ones of the ilk that Kerry beautifully illustrated to these incredibly detailed ones. And, you know, there are sort of nice three-dimensional diagrams that you can use in terms of detail and insight and other aspects. You know, it's clear that you build up insight more at the end of the simple or conceptual models, but you can verify with actual observations better at the end of the very detailed ones. So I think you know, it's fairly inescapable faced with a plethora of phenomenal processes, whatever, that we have to face to use to exploit this good hierarchy. And again, I would like to comment on something that Kerry said about communication. You know, quite clearly, we have to deal not just with the physical sciences, but and with the socioeconomic ones, but also with psychology. If you communicate the same, you know, if you communicate the same probabilistic forecast in the United States and in France, the reaction will be very different, because clearly, if you poll on optimism about the future of the next generation in this country and in France, faced with the same economic situation, okay, people will act, you know, very, very differently. So, you know, this is a whole range of questions that I can't explain. Now, coming back to the question that Kerry asked me to sort of address, quite clearly, stochastic, you know, nature is not, there used to be an argument in meteorology view and the hustle view. Lorentz point of view is that a lot of the irregularity that we observe has to do with deterministic nonlinearity. And so the hustle point of view is, well, deterministic linear is okay as long as you add some norms. And quite clearly, nature is not deterministic or stochastic. Nature is whatever it is. It's just our way of thinking about it. To speak in mathematical terms, the map between the world inside our head and the world out there, assuming it exists. It's this map which is deterministic, nonlinear, stochastic, whatever. And clearly, I think that the future is both deterministic, nonlinear, and stochastic. And so on. And aside from myself, there's another gentleman who is in this room working on this. Adding these uncertainties in a stochastic form intrinsically into the models. I thought, Kerry, you did some work, something for me, along those lines. And David Nealon, who isn't here, with a student of his who is in Illinois, did work along those lines, as well as Tim. And it's really very important to understand in a systematic way, not just how a particular stochastic parameterization improves something, but how it affects the entire behavior of the model. And yes, I will talk about that tomorrow.
Not a question, really, a further elaborate. So I'm Andy Maida from the Karate Institute. Further elaboration on what Kerry was asking Michael. So there was a large meeting of about 250 people at ECMWF, sponsored by ECMWF, Thorpex, and the World Climate Research Program this summer, and the topic was stochastic parameterization. So I think one shouldn't feel, I agree with what Michael said. I also agree with what a statistician said. A famous statistician, Bach, said, all models are wrong, some models are useful. And we should keep that in mind in all of our discussion. But for example, when Kerry mentioned the skill scores of ECMWF, they have essentially a user-blind stochastic strategy. They take all the nonlinear tendency terms and multiply by random numbers between -1 and 1, and call that their stochastic parameterization. Remarkably enough, that has fantastic skill for the mid-latitude teleconnections and the inverse cascades, the Pacific North America and the North Atlantic Oscillation. The skill scores over Europe, for example, are improved dramatically, and that's the skill scores they report. However, when you look at the tropics, which is one of the 800-pound gorillas of climate change science right now, where things are done very badly by all the climate models and by all the forecasting models for longer-range forecasting, even short-range forecasting, you'll find those same stochastic effects because they don't seem to be trained well enough. Going back to Michael's points, will give very poor results. And a little bit of advertising. The two issues Kerry raised are exactly what I'll be talking about in 15-minute segments of my talk this afternoon, actually.
Can I throw out kind of a mega question that came, I thought, from both of your talks, which was this: how do you use this information, and how do we make better use of it? And I guess the question I would ask is I know, Kerry, you wrote even in public media about sort of hurricane forecast relative to Irene and so on. And I was wondering about the following scenario. Imagine that, let's say, Lower Manhattan had been evacuated on a weekday at costs of hundreds of millions of dollars, perhaps $1 billion, shutting down economic Manhattan, and the surge had not materialized. So, obviously, this would have generated a lot of questions. So I guess the question I'm asking, and it isn't one to which there's an answer, of course, immediate answer, but what directions do you think people should take to try to make more effective use, basically, of how do we do a better job of the science is presumably going to improve and will continue improving. And how do you make use of that in a useful sort of way? I mean, the old question is like, if you were dictator, what would you do? Type thing.
I mean, Plato's enlightened king.
Well, that's a question. Imagine so, we always give this very cheap cop-out is, oh, well, that's for elected officials to decide, which is the same as saying, well, we're not going to confront that question. Someone else's. So the interesting question to ask is, suppose, what would you say to them? The mayor says, Mayor Bloomberg says, I actually want to hear someone else's opinion. I want yours, Professor C. Emmanuel, what would you tell them? And Clinton, I was going to ask you the same question, of course, about Galveston Island and Galveston Island and Ike. So, I mean, you can take them in whichever turn you want. You're the governor of Texas.
Oops.
Yeah, what did Rick Perry say that?
Well, we actually faced this a little bit in Ike because I was working we have a pretty close relationship with the Division of Emergency Management.
They actually asked us to
run AdCirc in sort of forecast mode
not
to
to
help them,
replace,
not to replace, but the information that they're getting from NOAA, but just to sort of use it as another,
So
decision.
we provide them
So
information.
we provide them information with the caveat that there's a lot of uncertainty, and we pretty much have to rely on them to make a decision about how they use it.
I was pretty
I was pretty uncertain about the results because we hadn't really run hurricanes or cases extensively, especially many scenarios of hurricanes, such as we have a better idea of what's happening now. So I was a little bit hesitant in saying this is exactly what's going to happen, but it turned out that the model was pretty good.
Remember, the National Weather Service was saying that if people stayed on the coast, they faced, quote, certain death. And obviously the vast majority of people who tuned out that forecast did just fine. So it's clearly some major disconnect somewhere in the system. I don't know where.
Well, I don't know. That's a difficult question. I don't know how to.
I was just going to comment as a New Jersey resident. What happened is, it's Kerry's point. The track, it was an exceptionally broad storm and weak and very slow moving. So in places like New Jersey and upstate New York and Vermont, the track shifted. And the impact of the hurricane shifted. And that's an uncertainty. It's what Kerry said. You need more ensembles, more understanding of the different kinds of slow-moving and fast-moving storms and how much precipitation they make where. I wouldn't know how. It wasn't really a storm surge question.
Right.
But there was, although the storm surge didn't turn out to be an issue, it wouldn't take it very much more. So I think that's question is really important. I think the temptation for scientists like us is the goal, I think, in our mind, I think we need to say that was all of us, was let's give them the best PDF surge in Manhattan and coast real time. And we actually attempted to do that. We ran surge models on all the different forecasts, tracks, and different models in real time, and tried to do that. But the problem is, maybe this is what you're trying to accept, is it doesn't mean much. You give the PDF to a politician or an emergency manager, what do they do that? What we've learned is they can do what you hope that they can do. What we've learned is we have to go some steps beyond the complete picture of this life. With a 30% probability, this is what Manhattan will look like tomorrow, and we look at a picture of what parts of Manhattan are flooded, and so on, 20, 40, 50, and get together with economists to say, well, this is how much damage it will do, right? And this, by the way, is if you evacuate people, how much it will cost you to do that. At some point, the information has to be turned over to people who actually make decisions about evacuating. But we think it's our job to give them the science numbers, the physical science numbers and stuff. And what we learned over long experience, it doesn't work because it doesn't go far enough to help them interpret it. We have to bring in economics and so forth.
Yeah, I think that's where the joint needs to somehow be made much better in any kind of natural hazards thing, hurricanes being traumatic, of somehow doing something that they can usefully look at, and then to look at the costs and benefits of various strategies, and somehow we need to develop better ways of doing that.
That's it. No, this one is called risk analysis. I mean, it's different from what we do. University of Arizona. Risk analysis, I mean, you can come up with, say, look, if there's so much vaccine and you're vaccinated only 30% of the population, everybody's going to be fine. The politicians aren't going to react to that. They're going to make a risk analysis.
Right, but I'm saying that treating these as two entirely different branches of human activity is probably not a very good way to go. That these. I mean, I think Kerry is summarizing. You need.
What I'm saying is that we're just not trained in risk analysis. We're not in the business of risk analysis.
Michael's asking.
Yeah, I'm sorry I missed your talk yesterday, Seth, but it's very similar for earthquake prediction.
Right, of course.
The issue of the cost of what statisticians call false positives and false negatives, the failure to predict versus over-predicting. I mean, that is really an economic and socio-political issue. I mean, it goes, for instance, with the issue of what is the cost that you assign to a human life as opposed to loss of property. So these are really complex issues, and I think that to the extent that we heard that maybe, the DMS would become mathematical and statistical sciences, there is a way of reaching over in there. But I think it is very important to do these kinds of statistics of false positives versus false negatives, and for a particular forecasting scheme, that might involve hurricane prediction or coupled hurricane and surge prediction or whatever, and try to face these additional issues in as objective a way as possible. I mean, it becomes harder and harder as you move more into the socioeconomic and psychological realm and so on. So, but it's inescapable to the extent that we do want to do good. I mean, we do want to have fun, of course, that's why we do what we do, but we also want to do good. So.
Yeah, I think it will also become very clear in the whole climate debate. It's basically this, various strategies of dealing with climate change. What you can mitigate, what you can abate, what you should try to deal with, in various ways, and somehow, we need to get a great deal better at it. Because we're not giving, if you look at the climate debate, it's obviously even more heated and more complicated. But, it basically is a question about, how confident are you of certain things, and then how do you factor that into their expected consequences.
I just want to say that there are advanced statistical methods that do help you with a problem of small number of extreme events. Something called random forest that I learned from a leading statistician, which really helps you, evaluate predictors for various concepts. Very rare events.
Let me just add one small thing. I mean, there is a branch of mathematics, a branch of game theory that can be fruitfully applied to how people plan forecasts. It hasn't been very much in meteorology. And Hercules, in the aero context, about the insurance industry responds to seasonal forecasts. And it's very interesting. So I think it's an example of borrowing Michael's terminology, we can do something useful and have a lot of fun at the same time. So that's the word to the students.
Yeah, there's a good analogy with the earthquake problem, and there's some experience there that's mid-grade because there's a National Earthquake Prediction Evaluation Council, and there's some of the one for California. And in fact, they deal not so much with earthquake predictions, but imminent situations. A moderate-sized earthquake has happened near a place where a much bigger earthquake might happen. And typically there are probabilistic estimates of the chance of this bigger earthquake happening. And one of the goals of these two committees or councils is to forward that information to the people who would be responsible for making decisions. And the system works, I'd say, pretty poorly. It's not a well-organized communication between the scientific community and the emergency response community. But I think there are a couple of lessons that have come out of that. One of the lessons is that ultimately the decision about what to do is a political problem. And the scientists can provide the best information to the politicians, but the actual action involves a lot more than science, including costs and risk of lives and political costs, which has to be...
The risk of re-election or not.
Exactly. It has to be understood. And the other is that practice is really necessary. The National Earthquake Prediction Evaluation Council actually drafts some language that would be modified under particular circumstances to pass on to emergency response officials. And that's forwarded to the emergency response official so that they can look at it and say, what would I do if I got this with some numbers filled in? And it's really helpful to have this practice because often the message comes back from the emergency response community saying, this would cause chaos. We don't have a way of addressing the kind of information that you're giving us. Here's what we need instead. And this requires some sort of continual feedback between different communities. And I'm simplifying to say that there's an emergency response person or agency that answers all these questions. It gets much deeper than that. But this sort of dialogue is really necessary so that when an urgent situation happens, people aren't totally confused about what to do.
Michael Stein in Chicago. I don't know everybody's background here, but I'm a little bit worried that we're the wrong set of people to be talking about policy issues. Obviously, they're that are important, but we see, my guess is we don't really have the right expertise for this. I was curious about you were discussing, this 15-second on a laptop model and this 2 days on a supercomputer model as two approaches to the problem. Obviously, there's a lot of room in between there for models that are maybe not quite so simple, but neither are they trying to do everything in high resolve, space and time scales. And I'm wondering, what are the things for kind of in-between models that would be useful? So they have some hope of running reasonable size ensembles, but not so simplified that they're leaving out a lot of the processes.
Well, I think personally there's a lot of room for intermediate models. And there's a direction that computational science is taking towards meteorology, and there's not as well. So the geology models by their level of sophistication. And when you read climate science literature, you get this impression of all kinds of things that built into these models. You can have plants respond, we can carbon dioxide. And you wonder, that we're focusing on a lot of details when the overall performance of the model hasn't evolved and obviate all of those things. So what you're saying might require really a cultural shift in our science. I'm not sure where to make. So the stress in the early pioneers of computational movement was to look forcefully, simplify ways, getting rid of stuff rather than putting stuff in. And with the advent of the explosive growth of computing, I think too quickly we throw away a lot of their discoveries. But what's the ideal coordinate system in these really great equations for application? And I don't mean spherical versus Cartesian. I mean mapping, for example, the equations themselves. The semi-geosciences literature, which hardly exists anymore, very big in the 70s and 80s. We're talking about mapping balanced equations and the coordinates, which not only have the advantages that I kind of stressed in resolution, but make the equations themselves simpler, because a lot of the non-linearity of the equation itself is absorbed in the math test. that whole argument seems to have gone away, it's in my field, and I think it's time to bring it back and ask, what's this, can we make some models that are accurate enough, but also fast enough to do large ensembles? It requires doing a lot of applied math, not just computational science back in.
Okay, let's take one more. Okay, let's take one more comment / questions. And then Mark.
I have one follow-up on this topic. I think other kinds of really depend on what we're trying to learn from this exercise. If we try to understand the basic physics, what's working really there, I would argue that supermodel is much better than very complicated models. But on the other hand, if you try to predict a certain place, how high the surge will be, then you need to take consideration of all the variations, the geometries, the bathymetry, all that. So you need to have complicated models. But then on the other hand, with that, you also have to worry about all the nonlinear physics or other uncertainties. So it becomes another question. With a sophisticated model also comes with a large uncertainty. So how do you assess the uncertainties and those with predictions and models? That's another challenge.
Yeah, I think that's a nice summary on which to end the session. So